And welcome. Thank you so much for listening in. In today's session, I will focus on the analysis phase of the safety life cycle, specifically the process hazard analysis, or PHA, and the layer of protection analysis, or LOPA. I will give you an overview on how to perform your PHA and LOPA, and then demonstrate how you can do this in exSILentia. First things first, please enable your speakers and mute your microphone. You can ask questions during the webinar by using the Q&A tab at the top of your screen, and I will take a look throughout the session to see if anybody has anything to say. My name is Kate Hildenbrandt. I'm a sales engineer with exida. My focus is to provide training and application support for customers using exSILentia and our other products. So basically, if you have any questions, concerns, you need support with your software, you can come to me and I will help you out. Today, I will give you some background on how your PHA and LOPA fit into the safety life cycle. I'll give you background on the strategy behind the methods of analysis, and I will show you a sample problem that will walk you through this analysis in our exSILentia tool. So let's start with an overview of the analysis phase of the safety life cycle. This is a very detailed overview of the first phase of the safety life cycle, starting with your initial process design and ending with your safety requirement specification. From this analysis, you can identify potential hazards and their consequence, as well as the likelihood of each consequence. Together, consequence and likelihood determine your risk. From there, you can identify layers of protection to reduce your risk. You want your actual risk to match your tolerable risk. If it doesn't, risk reduction is required. All of this information from your analysis goes into your safety requirement specification, which can help you when you move on to the realization phase to design your SIS, or your safety instrumented system. The safety life cycle summarizes the key tasks that are needed in this phase. So that includes your process hazard analysis, your layer of protection analysis, your SIL target selection, and your safety requirement specification. I'm going to focus today on the PHA and the LOPA, as we said. So what does your process hazard analysis entail? The objective per IEC 61511 is to determine what can go wrong. What are the sequence of events that could lead to a hazard? With the PHA, you can determine the risk and compare it to your risk tolerance to see if risk reduction is required. Finally, what safeguards can you put in place to reduce that risk? And are any of these safeguards considered SIFs, so safety instrumented functions? For instance, addition of a safety relief valve may successfully reduce your risk, but it's not required a SIF and therefore not part of your safety instrumented system. This is important when you go into the design phase. So to identify hazard scenarios, you want to make sure you have the right information on hand. This includes any info from previous studies. Perhaps you've already analyzed your site, or you have a similar site that you can use as a go-by. All of that information that you already put into analysis can be tremendously helpful. You also want to look at common hazards for your application and their consequences. Also, what safeguards have been used in the past to prevent consequence from occurring? Basically, you don't want to reinvent the wheel. If you have information that might help you, you want to have that on hand. To utilize one PHA method, you can do a HAZOP, which is a hazard and operability study, to evaluate your process. This is a commonly used method in the process industry. Following this method, you start by choosing a parameter. So your parameter could be pressure, temperature, flow. And you apply a challenge to that parameter. We call this a guide word. So that challenge might be more or less. How is this differentiating from your process? This establishes a deviation. Let's say our deviation is more pressure or high pressure. What could cause the high pressure in your system? from there, you can identify safeguards from this deviation. So if you have a deviation, that's going to have a consequence. You want to determine the severity of that consequence, and then what can we put in place to mitigate that hazard. You can also put in recommendations for the future. So once your PHA is complete, you can move on to your LOPA. The layer of protection analysis is a risk assessment method that takes into consideration the frequency of your initiating events, the likelihood of failure of your safeguards, the consequence severity, and the scenario risk compared to your tolerable risk. For the LOPA, we can quantify the risk and risk reduction to confirm that you have sufficient protection layers against your hazard scenario. I have a little example here for you. So this is a vessel filled with a potentially hazardous chemical, and in this case, we don't want the vessel to overflow or overpressure. So we have a number of protection layers here. It's color-coded. Hopefully you can see that. The first protection layer is your process control. So this would be your FIC or FIC. That would help you to close the valve on the inlet flow to the vessel. So the FIC will sense the flow and say that's too much, and it'll stop it. If that fails, you have a level switch. So as you can see, yellow, we want this level switch to sound an alarm, which will tell the operator that this yellow valve on the inlet needs to be closed. Your operator would hopefully respond, come out, manually close the valve, and mitigate the hazard. If he fails to do that, your next layer of protection is your safety instrumented system. In this case, it's another level switch, which is going to realize that your level is a little bit too high and automatically close the third valve on the inlet line. If all of these fail, you have a pressure relief valve at the top of the tank. And at the very worst case, if you have loss of containment, you have a dike at the bottom of the vessel to keep your chemicals from seeping into the environment. All of these layers of protection are very important, and as you can see, if one fails, hopefully there's another one in its place. So your LOPA provides a method to reduce accident frequency to something less than your initiating frequency. This method should produce consistent results for each hazard scenario. Here we want to emphasize how each protection layer reduces the frequency of the hazard event. We call these independent protection layers, or IPLs. They are used to evaluate the probability of failure on demand. This is a good measure of how effective your IPL is at protecting against the hazard. As you can see, the frequency of the hazard occurring decreases with each independent protection layer. I can show you how this is applied with an example. So to guide you through the PHA and the LOPA, I've put together a process, a sample batch reactor. So in this case, a little background so you know what I'm talking about. The batch reactor makes a product from the mixing of materials A and B in the presence of a catalyst that is contained in material B. The reaction is highly exothermic once it is initiated, but it requires a sufficient temperature for initiation to begin. During the reaction, there is some gas formation that must be vented. So again, that's just a little background. We do have a P&ID here. This is going to be your starting point, your process design. You can analyze this to see if the safeguards needed are in place. We do have a little bit to work with here. You can see we have a few interlocks, a few alarms already in place. We have an interlock that responds to temperature, an interlock that responds to high pressure, and an interlock that responds to the level going too high. There are also some simple process control loops. So let's say, as an example, what if the pressure gets too high in your reactor? what would cause the high pressure scenario? And what is the likelihood that that would happen? What are the consequences of the pressure getting too high, and how severe are the consequences? So would you have a lost time injury? Would you cause a fatality? How severe would that consequence be? And if it is severe, what safeguards should be put in place? So in the case of high pressure, this would happen in this sample problem if the PIC 500 did not work, that your vent valve to the incinerator is blocked. In this case, your PT 501 would sense that your pressure in the reactor is too high. This would enable interlock 3, which you can see in yellow. Interlock 3 does many things. It cools down the reactor by opening the valve for the chilled water to come into the reactor jacket. It closes the valve for hot water to get into the reactor jacket. It also closes the valve for feed B to enter the reactor so that your exothermic reaction stops. But the most important thing interlock 3 does is open XV500 to dump the reactor contents into the quench tank. This would be our SIF. It is the most direct reaction to the high pressure and would relieve it fast to mitigate the hazard. There are a couple other layers of protection here. You have your rupture disk PSE 500, which will lift at too high a pressure, and you also have a few high pressure alarms in place that would notify the operator that there is a problem, and hopefully he can respond. So after taking a good look at the P and ID, you can document your analysis in the PHA. I have a screenshot here of our exSILentia tool, which is called PHAx. It's one module in the exSILentia tool. In the screenshot, you can see that we have listed the cause, which would be that blocked vent valve, and we list the consequence. We have two consequences here. We have a safety consequence, which is overpressure in the reactor, which could cause an explosion. We have assigned it a severity, which I can show you in detail in the tool. I think 5 in this case would mean that you might have an on-site fatality. So your risk level based on your risk matrix is 20. That would be very high. In this case, we have the safeguards listed. Again, that rupture disk is number 1, interlock 3 is number 2, and we have 2 high pressure alarms as well. The second entry is loss of usable product. So this would be a business risk. The severity is a little less. We assumed you would lose a certain amount of money by losing your product. And the same safeguards are applied here. You can see that after the safeguards are listed, your likelihood of the event happening with those safeguards in place is less. Finally, we define hazard scenarios based off high-risk consequences. Each hazard scenario will be evaluated in the LOPA. And this is something I can show you better when I have the tool open. But at the end of the PHA, you link your information to the hazard scenario, and then you can import it into your LOPA. In that case, and I have another screenshot, this is your LOPA tool. In exSILentia, we call it LOPAx. Once you import your information in, your causes become initiating events and your safeguards become IPLs. So you can see your same safeguards, the 2 alarms, the rupture disk, and interlock 3 are all listed under independent protection layer. Your cause, blocked vent valve, is your initiating event. And the hazard scenario in this case is the runaway reaction from decomposition. You see at the top we have a target frequency and an actual frequency. We got this by assigning a frequency to the initiating event and assigning probability of failure on demand to each IPL. This calculates an actual frequency, which we want to match our target frequency. In this case, interlock 3, we've actually calculated the PFD so that it would match. So we know in that case what SIL level the SIF has to be at in order to design a safe system. So now that I've given you a primer on that, I'd like to open the tool and take a deeper dive into the analysis. So hopefully you can see exSILentia on your screen now. This is the dashboard. Mine is pretty clear. I have input the information already from the reactor problem here. So I want to show you first that we have some setup. You can click on your project configuration button, and I'm going to expand it. Here you can put in project information, you can name it, put in a description. We have pre-populated plant types and nodes. You don't have to use these, but hopefully they'll help guide you through your analysis if it applies to your application. So for each node, we have pre-populated a set of smart deviations. And again, as we talked about, a deviation is any change to your system that could cause a hazard. We want to help the user to consider all of these scenarios. So we have them pre-populated here, and they differ depending on the node and what's going on in your system. We also have some suggested safeguards, recommendations, and references. However, all of this is customizable, and you can put in extras that apply to your specific site. For instance, if you have your PNID, you can upload it, link it here, and use that as a reference. We also have suggested team roles, etc. You can input team members. I don't have any here, so that's not exciting, but you can input team members, you can put in their contact information, you can invite them to sessions, and you can give them action items. If you put a recommendation into your process hazard analysis, you can assign it to a team member, you can give them a due date, and update the status of that recommendation. You can also do your risk configuration here. So here we have 3 risk categories. We have business, environmental, and safety. During your analysis, as you brainstorm, you want to consider each of these. Make sure that obviously the people on your site are safe, but that you're not harming the environment and not adding business risk to your process. So obviously your process is going to produce a product, and you want that to be successfully sold and make money. So that is another thing we look at. We do have a severity matrix here, which shows the severity level and the tolerable frequency that goes along with that. Here you can see for each category what we would assume the level means. So we have a description. For your business category, number 1, you have negligible impact, and as you see, the cost of the hazard goes up as the severity level goes up. But for safety, instead of a monetary cost attributed to the hazard, it is an injury or a fatality. So these are the things you want to guard against, and you can, in your analysis, assign the severity level to indicate that this is what could happen. We also have a likelihood matrix. Likelihood, in the case I'm going to show you, is going to be analyzed quantitatively, so that's going to be your frequency. You can analyze it qualitatively, but here we're going to input values for frequency. You can see that here. And then here's your risk matrix. You see likelihood versus severity. This can be customized to suit your application. You can change the axes, you can add columns and rows. It's pretty limitless. So we want this to work for whatever you're doing. So now that we've gone over all the configuration, I can take you into my PHA. Here we have the unit is the entire PNID that you saw, chemical batch reactor. The node I want to focus on is the reactor. We have a couple other nodes. There was a condenser, a pump, and the quench tank. However, I did not analyze them here. We want to focus on what could happen to the reactor. The deviation here is high pressure. As you can see, we've considered high temperature, high level, no mixing, all sorts of things. In some cases, a deviation might not apply, and so you can go in and just check that. You can go in here and say it has no issues. And what's nice about this is you could delete it, but you kind of want to document that it was considered at all. And you can do that by just clicking no issues. If we go back to high pressure, this looks familiar because you saw it in the screenshot. We have the cause, which is the blocked vent valve to the incinerator. You have your two consequences. So overpressure in the reactor is a safety concern. It's also a business concern because you've lost your usable product. You have your safeguards. So we have the rupture disk, the interlock, the high pressure alarm, and the high pressure alarm. So in this case, I couldn't open this for you earlier, but you can switch to safety. Well, you can switch to safety, environment, or business right here. You do have your severity level, so here we chose 5, which means that we think that if the reactor exploded, you could have on-site fatalities. But you could switch this to lost time, injury, anything. And then that should give you your risk. Here it's saying it's 20, it's pretty high risk. So once we put our safeguards in place, we determine that the likelihood of this happening has been reduced to 2, and your risk is mitigated somewhat. Here you can put in a recommendation. I have not done that, but again, you can assign it to a team member, you can give it a due date, and see what the status is of that assignment. Finally, you can link this to your LOPA. So you can say, yes, I want to analyze this information in my LOPA and assign a hazard scenario to it. Here we have runaway reaction from decomposition. This high pressure scenario is included in your hazard scenario, but so is high temperature. A number of things can lead to this runaway reaction from decomposition, and all of those can then be analyzed in your LOPA. So what's cool about this is once you're done with your PHA, you've brainstormed everything that could happen and input all of your safeguards you have to date, you can start your LOPA. My LOPA is already pre-populated, but the way I did that is to push this button. This loads the data from the PHA into your LOPA sheet. You don't have to re-enter anything. As you can see, my runaway reaction from decomposition is my only hazard scenario here. My cause, blocked vent valve, became my initiating event, and my safeguards became my independent protection layers. At this point, and the numbers are already in here, but you would assign a frequency to your initiating event. There is a database here full of frequencies that might be useful to you, or you can input it yourself. And then for each independent protection layer, we put in a probability of failure on demand. So that is input here. You can put in your tag number, the category of your independent protection layer, your set point, anything that you find to be useful. Now here we have 1 for your high pressure alarm. We have 1. We assume that the operator could not respond to this if he failed to respond to the first one. They're not independent alarms. And we have a relief device here in our rupture disk. Finally, for our interlock, which includes our SIF, we have asked it to calculate the probability of failure on demand. So what this does is it ensures that your actual frequency will match your target frequency. And by doing this, it lets you know what your probability of failure should be. So here you have your calculated probability of failure on demand and your calculated risk reduction factor. This is going to go into your SRS and help you in your design phase when you are specifying the equipment in your safety instrument and function. So in this case, everything's good. Your target frequency matches your actual frequency, and you have information you can take to the realization phase of the safety life cycle and be sure that your system is properly evaluated and safe. So that is PHAx and LOPAx in a nutshell. To summarize all of this, let's review what we've learned about these methods of analysis. The PHA and the LOPA are key tasks in the safety life cycle. Information gathered in this stage is used throughout the life cycle to define your safety instrumented system. exSILentia simplifies this analysis and allows for easy flow of data from one step to the next. So like I said, you can take the information entered into your PHA, import it into the LOPA, import it into your safety requirement specification. This is going to save you time and therefore save you money. As I've mentioned, PHAx and LOPAx are just two modules out of many provided under the umbrella of exSILentia. exSILentia works to guide you through the entire life cycle. So the remainder of the analysis phase includes your SIL selection and your safety requirement specification. For the realization phase, we have Silver, which is your SIL verification tool, which is where you specify your equipment, make sure that your safety instrumented functions are safe enough, basically. And for the operation phase, we have our life event recording tool, SILstat. So you can go from A to Z with exSILentia to ensure the safety of your site. I have a little background on exida here. You may have seen this slide many times if you are frequently listening into our webinars. But we have locations all over the world. I work out of Sellersville, PA, where our tools are developed and maintained. You can, again, email me if you have any questions. I can answer your questions myself or get you answers from those in the know. And hopefully you are aware that exida offers many products and services. We do functional safety consulting, product certification. We do a lot of training on these topics. We have textbooks and other reference materials, tutorials, databases to help you that offer data that can help you with your analysis phase or anything you might need to do. And we also have professional certification, so if you want to be a CFSC or CFSP, we can help you with that. So at this juncture, I'm going to take a look at the questions, see if anyone had